Perfect. So thank you very much for that kind introduction, and thank you very much for the organizers for inviting me to talk. So what I'm going to talk about today is about quasi-periodically driven system and how we can realize interesting new dynamic phases in those quasi-periodically driven systems. So the talk is going to sort of be structured in two parts. So one of it is going to be a theory component, and unusually for me, one of them is also going to be an experimental component. And I really want to thank my collaborators who've worked with me on this over the years. On the theory side, Dominic, Wenwei, Ajesh, Drew, and Romain. And on the experimental side, the entire Honeywell group, Honeywell Quantum System, who actually built the machine on which we run the experiment. So just to give a very quick sort of setting the stage and background, we're interested here in universality in systems very far from equilibrium. And the very specific conditions I want to require is I want to consider a closed system that undergoes unitary evolution. It's quantum, it's many body, there are interactions, but those interactions are local. And there is an external drive, so there is some coupling to that external system, but that's going to be constrained to be local and unitary. And so we're really trying to understand what happens if under time evolution, if we start with some initial state that's local that we can prepare in the lab, we time evolve it. Where does it end? What are the universal features? And why are we interested in this? Well, it's an interesting theoretical problem, but there are also many interesting experimental devices that are being developed, which really try and reach this regime. And so we can try and test those experiments, those ideas in the lab. So as a very sort of crude cartoon, what we would expect in the generic system in sort of a textbook setting is that if we have local external driving to a system, it'll initially evolve coherently, and then it'll start eating the energy that you drive to the system and then heat up. And something that we've learned, and that's very interesting, is that even as the system heats and even if there are no actual symmetries in the system, you still can get some very interesting hydrodynamic behavior due to the entanglement constraints of the entanglement that come from the fact that this is a locally interacting and locally driven system. But something that we want to do is we want phases or dynamic regimes that are more interesting than heating. So we somehow have to stop that heating or at least delay it up to a very long time. And so this is just a generic cartoon. We have to do something to introduce an additional regime that I'm going to call preheating. And I'm going to use the word preheating throughout because this state here could be itself thermal. It could be a Gibbs state. It could be an MBL state or a glassy state or quantum coherent. There are very many different properties, and it could be more general than sort of pre-thermal, which is sort of also often used as a wording. Okay, so with this state set, I want to very quickly review some of the ideas that were there in Floquet driving, because the quasi-periodically driven systems are going to try and generalize a lot of the same notions. So in the Floquet driven system, we've known for a couple of years now that there are different strategies to realize such a preheating regime. And I'm going to focus on just two. One of them is high frequency driving. Right? So the regime I really want to consider here is that we have our interacting many-body system. It has some local energy scale J. You can think of this as a site or a cluster of sites that couple to an external drive that's done at frequency omega. And provided that we're in the regime where the driving frequency is much bigger than the local interaction scale, then we can actually delay this heating, even if the driving is much, much less than the actual many-body bandwidth. So how does this work? Well, if we have this, imagine this little picture where here I'm plotting the many-body energy, and here's some sort of effective band of scale J made by the degrees of freedom on this local site. If I then have my external photons from the drive that can be absorbed or emitted, you can see that actually I need to absorb in order to absorb one of these photons, I need very many processes J that flip local sites. Right? So maybe to make a short linear response argument, in order to connect different states of delta E with that drive, this requires rearranging very many local sites of the order of delta E over J. And so this is a process that is then exponential in delta E over J, because I basically have to do something at sort of n delta E over J times in perturbation theory. And so this actually bounds the heating time to be exponential because, and delta E is just an omega. And so now we get an exponential regime where heating is delayed, and that's a bound we can place on that heating. One thing that's very important here is that you can also see that there really is a big gap, right? There's a sort of, regardless of actually what the form of the matrix elements are and what the spectral content is, there's always sort of a minimum omega gap in this case that you need to overcome by rearranging many sets. The other way we know how to avoid heating is by adding strong spatial disorder. And so here, the energy scale, local energy scale is the big local disorder scale, W. And then it has been shown that actually we can realize MBL, and MBL is extra special because it has been shown that for rapid drives, MBL is stable up to an indefinite time, basically for the same arguments that people use to justify the existence of MBL in the first place. Okay, so here we have two different ways of realizing a preheating regime. I'm mostly going to focus on the high frequency driving, at least for the conceptual part, and we'll come back to a disorder right at the end. So once we have this preheating regime, well, there are very many interesting things that we can do in it. So for example, we can realize new types of phases. So if we have a very simple preheating regime, then the Floquet unitary, which is the single time evolution during that during one Floquet period, is actually equal to some effective local static Hamiltonian. I just want to make a technical point here. This decomposition is very different from the Floquet theorem, right? So Floquet theorem does tell us that there always is a matrix in a finite dimensional Hilbert space for which this is true, except in general, this matrix is horribly long local. And we know that has to be the case because this holds true for all times, including those times where the system heats up to a featureless infinite state. Okay, but here in the preheating regime, we have an effective local Hamiltonian that really looks like an effective local Hamiltonian you would write down. And something that people have been very interested is to realize new types of phases. And one of those types of phases goes under the name of Floquet engineering, which basically means that your effective Hamiltonian describes a phase that is topologically non-trivial in the sense that the Hamiltonian cannot be deformed to a trivial Hamiltonian. But there's something more dramatic that can happen in these dynamic phases, which is you can realize a drive which is intrinsically non-equilibrium in the sense that you can never deform it to an equilibrium problem, no matter what the Hamiltonian. And to be specific, what you can show is that you can find forms of this Floquet unitary that are equal to some big operator X, in addition to some effective static local Hamiltonian evolution. And the fact that there's a big operator X that cannot be written in any way as an exponential means this is never deformable to a situation that you can get in a static Hamiltonian case. And so here X to the power of n is the identity. That's a way of saying it's a big object. And the existence of this X is not accidental. It really is actually a reflection of the time translational invariance of the Floquet system in a way that I'll also make more precise in a couple of slides. But for now, we just have this decomposition. This operator is X is big, and so we can get lots of interesting phases from this. For example, we can get time crystalline phases, where basically this operator X acts as a global knot rotation on your system that breaks the symmetry, and so your system starts flipping back and forth at double the rate, say, of your drive. You can get Floquet SBTs, where this X corresponds to a charge pump that pumps a charge pair on two opposite sides of your system, or you can get chiral Floquet phases where you have little quantum information that sort of marches around a two-dimensional system as pictured here. Okay, so this is sort of setting the stage for what we know about Floquet phases. And now I want to generalize this and talk about quasi-periodic driving. So what do I mean by quasi-periodic driving? Well, now we have multiple frequencies instead of just sort of a single frequency and harmonics as in Floquet. And those multiple frequencies are irrationally unrelated, which means that there's no integer vector for this to be true. For the purposes of this talk, I'm basically going to reduce everything to the two frequency case, where you can just think of the ratio of these frequencies as being irrational. And one way we're going to construct this Hamiltonian is by thinking about it in a higher dimensional space, where there's some sort of higher dimensional object which lives on a periodic lattice, and we're going to take a cut through that periodic lattice at an irrational angle. Right? And the fact that it's an irrational angle means that the pattern will never repeat itself in actual physical time, but it still sort of has a lot of, inherits a lot of special properties because it's derived from a higher dimensional periodic lattice. Here I've sort of drawn it in the extended zone scheme. Of course, there's also a single unit cell drawn here, and we can fold the path of the Hamiltonian back onto the unit cell if we want to do that. Okay, so quasi-periodic structures are very interesting. There's been a very long history of quasicrystals in space. I know that's something that a lot of people also at this conference have been working on. But let me make some general statements about quasi-periodic time evolution. And the most important of those statements is that there's only one physical time, and that physical time is time ordered. Right. So this is a very important sort of contrast to the quasicrystal case. So if you imagine back to maybe the picture that many of you have seen of the standard cut and project method of how to get a one-dimensional quasicrystal from a two-dimensional pattern, take an irrational angle, project some lines, or if you remember back to Uli's nice experimental talk where they had two spatial lattices that were superimposed, then here this sort of works, conceptually. Is a little bit easier than the time-evolved case, basically because the position of all these sites commute. Whereas if you think about this Hamiltonian as a function of time in this higher dimensional space, the Hamiltonian at different times do not commute, right? And we have to ensure that this time order is actually satisfied. That leads to very interesting effects, and we'll come back to that later. H of t, the physical time Hamiltonian, has absolutely no time translational symmetry. And there's no equivalent of the Floquet unitary here. There's no single time unit or single unitary operator, which is static, that we want to study. Now, quasi-periodic evolution has had a very long history, and a lot of people have considered it, especially in few-body systems. And one of the most important results from Jocelyn and Leibovitz from the 90s is that, in general, quasi-periodic evolution does not have a quasi-periodic decomposition. And there's no analog of Floquet's theorem where we can write down some sort of effective decomposition with some operator P here, which is quasi-periodic in a static evolution. What they've also shown as a part of it is that even in few-body systems under quasi-periodic drive can, under certain conditions, be ergodic, or sorry, I should say chaotic, in their manifolds of space. So the number of ways a quasi-periodic system can heat and destroy any structure are very, very large. Nonetheless, and this is basically where our work comes in, there are still regions where we can sort of get such effective descriptions. And again, we're going to turn to the high frequency limit to describe those. So one thing you could immediately think about is that if you just look at the problem naively or in perturbation theory, you could be confronted with lots and lots of divergences and runaway heating. And the way to think about this is that now we have two incommensurate frequencies. We can make up any energy difference we want from those two incommensurate frequencies, which in particular means that we can hit any resonance, and you could imagine that we just heat, and that's the end of that. So just to come back to the analogous of the picture I had before, in the Floquet case, we had this nice finite gap of a minimum frequency that set a minimum number of excitations or sort of rearrangements of J that we needed. Now with the Floquet case, the spectrum is dense and okay. But of course, that's not the end of the story. Because of this higher dimensional structure, the photon spectrum of emission absorption is actually highly structured. And there's a hope that that high degree of structure sort of interplays in a slightly more subtle way with the different absorption. So let me go back to a sort of linear response argument and walk you through how we can get a preheating regime also in the quasi-periodic case. So we're still in the case that we're absorbing and emitting photons, and we're still in the case that we are going to require rearranging delta E over J sites in some perturbation theory process. But now what's different is that we need to bound the number of different processes of absorbing and emitting different photons that can actually give us this delta E rearrangement. And that bound comes from a Diophantine-like equation, which you can very loosely think of some sort of density of states argument, where for almost all frequency vectors, omega, there's some relationship between the number of n I'm sorry, I should say that for almost all frequency vectors, omega and vectors n, there's a relationship that bounds this magnitude in terms of the magnitude of n, of the sort of the size of the number of photons in each direction you admit. So if we take this bound and put it into our heating rate, which is again exponential in delta E over J, you can see that this is bounded by something which goes by omega divided by n to some power. And m here is the number of independent, sort of irrationally independent photon frequencies. So what you can see by looking at this is that if we have processes with a very large n, which corresponds to absorbing and emitting a very large number of processes, this will this 1 over n will go to 0, which means that our heating time essentially has no bound. And that corresponds to the fact that the system will heat extremely quickly. So in order to actually delay that onset of heating, we have to do something that we didn't have to do for Floquet, which is we have to make assumptions about the actual spectral content of our drive. So in particular, our drive has to be bounded, the modes of our drive have to be bounded and suppressed at very large n. And for the calculation that we did, we assumed that that's smooth and exponential suppression at large n. And if we put that in and do sort of a saddle point estimate of the heating time, then we actually find a stretched exponential form. The stretched exponential form is nice. It reduces to the Floquet case when we only have one single frequency, m equals 1. But it tells us that provided that our drives are sufficiently smooth, we still have a parametrically long preheating regime. Now, very quick caveat, if you have a system which is completely finite, which is sort of compactly supported drive, which is super smooth, then actually you can even get times that are longer than that, provided that you don't generate higher harmonics during your drive. But that is a technical comment that I can answer questions to if people want. Wonderful. So now we have a regime where we can at least hope, a preheating regime where we can have a bounded sort of, we have a lower bound on the heating time, which means that once again we can try and realize interesting dynamic phases. And I'm just going to quickly summarize a lot of those results in one slide without going into the technical details. So first of all, we can make the argument, the linear response argument on heating rigorous to all orders. And that's basically a combination of the proof by Aban and Dirac, Uveniers, and Wenwei Ho, together with kind of the symmetry construction by Elsevier and Nyack, and sort of order by order in some high frequency expansion, we can actually rigorously bound the heating rate. And what we get when we do that rigorous bound is that actually we can derive in this preheating regime a quasi-periodic decomposition, where the effective unitary can be decomposed into a quasi-periodic operator P, as well as some static local Hamiltonian evolution. I've sort of sketched this as a cartoon, and just to make sure this is, to say this explicitly, this is not simulated data, this is just a cartoon, but the picture that we get is that we have some initial transient time where the system is coherent, and then it enters this preheating regime that may, for example, be a Gibbs state until we hit this stretched exponential heating time, and the system generically will decay. And during this preheating regime, we have quasi-periodic oscillation in the system. But just like in the Floquet case, we can have something more exciting. We can have a different type of high frequency regime where we get new emergent symmetries. And in fact, those emergent symmetries reflect the multiple time translational symmetries of the drive. So to be specific, there, just like in the Floquet case, we had this X operator, which was a reflection of the discrete time translational symmetry of the periodic drive. We can have a high frequency decomposition where we have an additional U operator, which is quasi-periodic, but it's quasi-periodic on a different lattice than the original Hamiltonian. So I've sketched this here. If you imagine our original quasi-periodic Hamiltonian as being derived from this square lattice, or where the black box is sort of the little red square I drew up here, then we can get an effective time evolution with an operator here, which is quasi-periodic on a different sublattice, say this rectangle, this sort of rhomboid sublattice. And so now we have something where we have an emergent symmetries that are sort of multiple emergent symmetries corresponding to the multiple different symmetries of the underlying Hamiltonian. And these really act like sort of multiple time translation symmetries, which is quite surprising because there is only one physical time. but this just happens because of the action of these operators in this preheating regime. So once we have these extra symmetries, we can do topological classifications on them. We can build new types of symmetry breaking phases like time-quasicrystals. We can have quasiperiodic SPTs and many other interesting phenomena. So in the last couple of minutes, I want to just shift gear quick and talk about an experimental realization. And so this is something that we did together with the group at Honeywell, where we essentially realized a quasi-periodically driven system on their so-called H1 system, which is 10 trapped ion qubits. The sequence that we're going to use, because it's a discrete quantum computer, is going to be made of sort of discrete pulses, and we're going to choose a Fibonacci sequence. Right, the Fibonacci sequence has a recursive pattern, and it's made up of two incommensurate frequencies, one in the golden ratio. Because of the discreteness of these different gates, we're actually going to be less smooth than some of the bounds I presented. But these types of Fibonacci drives is something that me and Romain and Drew studied a couple of years back, and there's still a preheating regimes even in those drives, and I can comment more on that later. The specific form of the gates that we choose is basically an AKLT-like sequence. I'm going to go through the gates in just a moment. It's something that was sort of proposed by Aaron Friedman, Braden Ware, Romain, and Drew, but we are here taking a slightly modified version of the drive they studied. The drive that we have here is we have two different unitaries, X and Z. They consist of Ising gates that are uniform. And then we have Ising gates that are bond disordered. So these different Ks respond to some different disorder. And then finally, for each of these sequences, we have a random magnetic field or random one-side gate that applies on all these spins that essentially applies a disorder, but that disorder is random and does not preserve any symmetry of the system. Similarly, we have a second gate, the Z gate, which has the same structure, except where the bonds are along the Z direction. Again, we have a random disordered pattern. This pattern is different than the original pattern. So what you can see is that there's actually no symmetry left in the system whatsoever. But what we're going to find is that there are two emergent Z2 symmetries corresponding to an operator, which is almost the product of all x's up to some small rotation, and a GZ that's almost the product of all Z. And those two operators will be the action of the two time translations in the different time translation axes. Even though this has a different driving structure, this recursive structure actually allows us to write down the full decomposition using that sort of recursive Magnus structure that we explored in this paper. Okay, so how does the data look like if we actually run the sequence? So here I'm showing you the actual data from the device, plotted in logarithmic time or Fibonacci time. And the reason I plotted in Fibonacci time is that the quasi-periodic pattern becomes a very simple three-stage recurrence in logarithmic time. And what you can see here is an XX correlator, with the blue being the XX correlator on the boundary, and the orange being the XX correlator in time averaged over different bulk states. And here we have the ZZ correlator on the boundary and the ZZ correlator averaged over the bulk. And we're going to evolve this up to this Fibonacci time 9, which corresponds to a physical number of different layers of 65, which for those people who are interested in quantum computing corresponds to about 2 qubit gates per site, which is actually quite a long time for current devices. Back to the physics. What we see is this orange dashed line is the simulation that we have for the system with a 1 qubit and 2 qubit fidelities of the machine put in as noise. And we see that that actually very accurately describes the system, and the bulk decays basically to some featureless state very quickly. The edge modes, on the other hand, show this persistent oscillation with a decay, slight decay, that is completely captured by the 1, 2, and 2 qubit incoherent errors. And so what that means is that we're actually seeing these long-lived oscillation of some dynamic edge state coming from our quasi-periodic time evolution that sort of rotate quasi-periodically on the boundary. Again, the point I really want to make is that there is absolutely no symmetry in this problem microscopically. There's no Z2 symmetry that we would normally require to realize a Floquet SPT. the symmetry that protects these emergent edge spins and this topological phase are purely coming from the quasi-periodic nature of the drive and these two emergent time directions. Here's another plot showing the edge states. Here we're detuning a parameter, the parameter J, away from the ideal limit, where we're going away from sort of the perfect, sort of a perfect pulse limit, and we're slowly, as you can see in this green line, entering a regime where the topology, which is not topological anymore, and sort of here we're on the phase boundary. Let me just re-emphasize the importance of these two emergent symmetries by contrasting this to the case where we did the sort of a very similar experiment, but with a Floquet SBT. And in the Floquet SBT, we have a periodic pattern of a single unitary U with a very, very similar drive. Here we actually consider an XY drive and a site a magnetic field that is only in the X direction. And because the site magnetic field is only in the X direction, this random disorder, you actually have a Z2 symmetry, which corresponds to flipping around the X direction. So if we look at the data here, then the bulk data, which is again the orange one, has slowly decaying MBL because of the disorder. And it very perfectly, the decay of those MBL L bits very nicely matches the 1 particle and 2 particle incoherent error that the experimentalists have characterized this device with. And so both the X and the Z direction sort of really match that quite nicely. If we look at the edge states, the picture is very different. So in particular, you can see in the ZZ correlation function that we have this node here about time 20, where the signal is already decayed. And to make a long story short, this node corresponds, is a signal of, you can imagine, beating. This is actually a single disorder realization. So you can imagine a sort of a beating profile, with that beating profile coming from the fact that this microscopic Z2 symmetry is broken by coherent errors. Right? It's not a microscopic symmetry of the ions. It's something that's just approximate. And there's some stray static magnetic fields in the calibration that break that symmetry. So if you want to think about it, this procedure is actually an extremely nice and precise measurement of that coherent error, which we can use to characterize the system. But sort of from a physics and phase perspective, it sort of destroys the FSPT at this point. And so going back to the case, and again, this is at time 20, contrasting that back to the time 50 or almost 60, we can get where we still have a very strong signal in the quasi-periodic case. Just goes to highlight the fact that if we have symmetries that emerge from the drive themselves, they are much more robust to coherent errors than sort of microscopic symmetries that are only approximate. I should also mention there's been a recent paper by a group to realize a very similar FSBT in superconducting qubits, and because of the superconducting nature of them, they have different symmetry properties. So I just want to point out this paper. So with that, let me summarize and sort of give you the main takeaway message. The main takeaway message is that complicated drives still have a lot of universal generic structure. So we started off with the idea that quasi-periodic drives, because they're incommensurate, will just kind of heat, and that's the end of that story. But that's not true. And so these dynamic symmetries and phases that can emerge are really kind of interesting, and we can ask the question, how far can we generalize this, and how far can we generalize the new phenomenon that we've seen? Can we add even more complicated drives? Can we even take away less structure out of the or less constraints out of the drive and still have interesting non-heating regimes? For quasi-periodic systems specifically, there are lots of open questions. There's questions about how to numerically simulate this, especially beyond the heating bound. We can imagine that if we add disorder and have some sort of quasi-periodic MBL, is that stable for all times? Do we know? How would it decay? There are other quasi-periodic phases that there are other phases have been discussed for Floquet phases, like chiral phases. Do generalizations to quasi-periodic drives exist? Can we, have bounds with step drives, long-range interactions, and finally, can we connect these ideas of quasi-periodic topological phases to some sort of quantum error correction? And so with that, I want to say thank you very much and take any questions.